Welcome to the first video of our discussion of SNAc reactions. Oh, no, we already did that. This is the first video of SLO7. Sorry. But we're going to talk about things that look a little bit like SNAc reactions, so you can understand my confusion. What I'm showing you here is the mechanistic kind of picture that you would have expected for a classical SNAc reaction. I've kept things generic. Things are labeled to help you. We've got our electrophilic carbonyl. We've got an addition step to make a tetrahedral intermediate. That tetrahedral intermediate can undergo elimination where a leaving group is lost to make the substitution product. This is all looking kind of vaguely familiar. You know, a lot has happened. I know it feels like we've all lived about a decade since we talked about this in class. But what I want you to do to get started here is to think about doing this experiment. Imagine you mix these two compounds together, and then you maybe are taking NMR or TLC while the reaction's going. And it turns out that there's actually 3 different possible outcomes that you could observe from this kind of a reaction. 3 different kinds of compounds you could see as the reaction goes forward and things start accumulating in your flask. So just go ahead and pause your video and come up with the 3 possible outcomes. Like, what might you observe? What are the options? All right, so you've got some options, right? You could think about what might happen if you were to do this reaction. The most obvious to me is that we would make the final product. We'd do a SNAc reaction, we'd make our substitution product. Hooray, we get paid, that's awesome. But there's actually 2 other outcomes that are a little bit less obvious, or maybe one is so obvious that you didn't think about it, and that's that nothing might happen at all. You might end up with just the starting materials left over. That actually happens a depressing amount of the time when we try to do chemistry. And the third option is that you could actually end up accumulating the tetrahedral intermediate itself. So we've got 3 different viable outcomes for this kind of reaction. We've got like the classical SNAc. That would be where we make the products on the far right. We've got what I'm going to call an irreversible addition. This is the case where we actually accumulate tetrahedral intermediate. So implied in this type of language about an irreversible addition is that the elimination step can't happen for some reason. So we can go here, and then we get stuck. And then the last outcome was what I'm going to call a reversible addition. And so the idea here is that this process can happen. The elimination, for whatever reason, cannot happen or does not happen. But this addition is actually unfavorable. So even though we make small amounts of the tetrahedral intermediate, as soon as it forms, we go backwards. Right? So those are kind of our 3 possible outcomes, and it would be useful for us to be able to predict, looking at the structures that we're given, whether one of these outcomes is most likely. So one of these kinds of analyses we've already done previously in the semester, we can make predictions about whether the SNAc reaction will be, like the total of both addition and elimination, will be favorable. So we can predict when the leaving group anion is more stable than the nucleophile. And I know that some of you like to actually look at stabilities of carbonyl versus the other carbonyl. That's fine too. So you could write that, if you're taking notes, you can write that here. I want to focus on anions because it'll actually be a unified framework for us to look at these other 2 cases. We know that these equilibria, either for addition or for elimination, that those are governed by stabilities. Nature being, well, you know, is just going to pick the structures that are most stable. So what we're saying our outcomes are essentially are related to, are these structures most stable? Is this structure most stable? Or are these structures most stable? So in our analysis for the SNAc reaction, we basically are assuming that the tetrahedral intermediate is less stable than both reactant and product. A lot of times that's true, but it's not universally true. So let's think about a hypothetical scenario where we would actually do an irreversible addition, right? So remember that I'm describing here that this happens favorably, but this does not. So we could say a few things, right? The irreversible addition is predicted when our nucleophile anion is less stable than O minus. So basically we're saying nucleophile anion is worse than O minus. That should give us a driving force to get to the tetrahedral intermediate. And that's not enough though. We also have to incorporate some types of information about O minus versus the leaving group. We have to explain why when we get here, we don't also eliminate. So when nucleophile is less stable than O minus, and O minus is more stable, than Lg minus. Both of those conditions need to be true to do an irreversible addition, right? I basically need to create a position of stability in the tetrahedral intermediate where I go from addition, like through the addition favorably to the tetrahedral intermediate, and then I get stuck down here where I can't get back out. I have to go too high up in energy to get back to the elimination products. Okay, so then the other possibility is this reversible addition. So what I'd like for you to do is basically you can see how these kinds of statements are constructed. We're comparing stabilities of anions. I want you to actually write a statement like this that predicts the reversible addition, where we really end up just staying right here, right? Maybe we can do the addition, but it's never favorable, right? Maybe we can do the elimination, but it's never favorable, and we just have this compound showing up at equilibrium. All right, so go ahead and pause your video and write a statement that corresponds to that kind of a process. Okay, so you have your statement. Again, what I want to think about is this idea that the nucleophile anion, if I'm ending up here at equilibrium, this nucleophile anion has to be the most stable of the three anions present, nuc minus, O minus, or Lg minus. So I could write something like, is predicted when nuc minus is more stable than O minus, or, I'm going to make that caps because it's important, or Lg minus. All right, so why did I capitalize or? Because you have two criteria that both have to be met. It has to be the case that the nucleophile anion is more stable than two different other anions, both the O minus and the Lg minus. And so the same thing is true here, two criteria. Right, so that's kind of important for us. Right, so we can see that this reversible addition case is going to show up under a very kind of highly predictable set of instances. And so now we can actually make predictions about where we're going to fall here just based off of your understanding of anion stability and also some data that corresponds with anion stability. Okay, so now that we've established the three kinds of outcomes that can exist when nucleophiles react with carbonyls, we could look at specific examples where we'll actually see each of those outcomes for like real reactions involving real compounds. So I haven't labeled them as our possible outcomes. I'd like for us to go through that together by actually assessing anion stabilities, and we'll just work this top problem first, where we're looking at the reaction of acetone. So this is a ketone reacting with a benzene ring with a negative charge, right? So this is like the phenyl anion. And we know that this should be a fairly good nucleophile. That would give us our tetrahedral intermediate shown here. Remember that pH is the same as a benzene ring. I'm just drawing it here like this to save space. And then finally, in principle, we should be able to break off one of these two methyl groups. That would be a leaving group. That would give us a CH3 minus and our substitution product. Okay, so what we need to know are anion stabilities. So we could do this qualitatively where we have phenyl minus, O minus, or methyl minus. Which of those do you think would be the most stable? You probably have an idea in your head. That's fine. We could also confirm that using some data where we would actually look at the pKa's of the conjugate acids of these structures. So the pKa of the conjugate acid of this compound would be for benzene itself, where there's a proton instead of where the negative charge is. And that pKa, so I'm going to write this as pKca, or pKa of the conjugate acid, is about 50. We could look at this anion. The pKca would be for a compound where there was a proton on the oxygen instead of an O-, so that sounds like an alcohol. This is one of the pKa values you should still have memorized. It's about 15. And then finally for methyl minus, this would be the pKa would be for methane, so CH4, or an alkane, and that's also about 50. So if I look at my options, one of my anions is way more stable than the other two. It's the O-, right? It's going to be way more stable to be this tetrahedral intermediate than to have to exist in a state where there's a phenyl minus or a methyl minus. So this is actually an example, this top reaction, of an irreversible addition. So here is our first example, irreversible addition. If you look carefully at this, it looks a little bit like a Grignard reaction. If I'd actually put NGBr on this carbon instead of a carbon minus, we'd get the same kind of reactivity, a carbon anion, and we would end up doing an addition. And then we know that those reactions, if you do them with ketones, they just do a single addition and stop, because the elimination here is to go from something that's a highly stabilized anion to something that is not. Right, so this is basically a SO6, an irreversible kind of addition. We could also look at this reaction here where we have the same electrophile, still acetone, but we've changed our nucleophile now. So this is the cyanide anion. There's a negative charge on this carbon. That makes it nucleophilic. So we could affect an addition to the carbonyl. That gives us our tetrahedral intermediate. And then in principle, this tetrahedral intermediate could eliminate a group. One of those possibilities is that Cn- comes back out. We go backwards. There are reversible additions. But there's also a possibility that we could lose a methyl group, which is what we would need to do if this were a SNAc reaction. We would need to actually exchange one of these groups for the nucleophile. So again, we could play our game. Which of these anions looks the most stable to you? You can use any kind of number of structural ideas that you want. I'd like for you actually to go ahead and give this a shot. Use what you know about structure and stability to predict which anion, this anion, or this anion you think is the most stable. So go ahead and pause your video and make that prediction now. Okay, so one thing you might have considered is that, well, oxygens are highly electronegative atoms. They're going to be good at stabilizing negative charge because of that. And so it would be reasonable to predict that the O- is, again, the most stable anion among the three possibilities. I'm sure you can reject CH3-. This is probably the least stable anion of my three in this series because there's no stabilizing features at all, and it's also a carbon. Cyanide's harder, though. It's definitely a carbon, which is not great, right? A carbon's not that electronegative. But we're directly attached to a nitrogen, so there should be quite a bit of inductive withdrawal from carbon to N, and that should actually stabilize its negative charge. One of the factors that we probably haven't really discussed much is the impact of hybridization. So this carbon is sp hybridized, which actually makes it very good at stabilizing electrons. We basically are saying you could put these electrons very close to the nucleus, much closer than you would necessarily expect. And so if you actually look at all of your pKa data, what we find is that the pKa for our tetrahedral intermediate is still about 15. It's not going to be the same as this structure. We know the nitrile will impact something, but we'll say it's about 15. Methyl is still methyl. Yes, I know. I'm waiting to actually label the one you're most curious about until the end. So this turns out to have a pKa of 9. Kind of surprising, right? So the conjugate acid of this structure is HCN, or hydrogen cyanide. So this is that compound I was telling you about that's a gas and is enormously toxic. But it smells a little bit like almonds, so at least you get to enjoy like praline flavor in your mouth while you're dying. Okay, so if we look at our pKa's here, the experiment actually might contradict what we would have predicted, but it turns out it doesn't contradict what happens when you actually mix cyanide with acetone. This addition is unfavorable because if I do the addition, I make a less stable anion than where I started. So we don't really do this. What I'm going to say, not as an X, is that we go predominantly backwards. And even if I ever get here, what's going to leave? Is it going to be cyanide, a highly stabilized anion, or methyl minus? Right, so the elimination is essentially not feasible at all. There's such a huge difference in stability between this negative charge, and this one, there's no reason that you would ever go down that path. So this looks like an example where we're looking at our reversible addition. It happens, but it's unfavorable, which is this SLO. And then finally, we could look at our third reaction here, and we'll play the same game. So our pKa now, again, we're using the same cyanide, so we know it's pKca already. And now we're using an acid chloride. That sounds a little bit like a tip-off about what might be happening here. Here's our tetrahedral intermediate. Again, it's going to be not the same as this or this, because now I've got a chlorine that's not present in either of these structures, but it'll be similar. So I'm going to call it about 15. Remember, we're rounding. And then again, here I've got Cl minus as a leaving group now. So the pKca here, we're describing HCl itself. So -6. So we've got a highly stabilized anion in the final products. So it looks to me like in this case, our initial addition is reversible, such that predominantly, if we get here, like this is less favorable, the tetrahedral intermediate is less favorable than the reactants. But when I get to the tetrahedral intermediate, I see this like land of milk and honey where I'm like, ooh, the best anion ever. And so this equilibrium lies very far to the right. This looks like a SNAc reaction, right? So even though this initial addition is unfavorable, I'm basically pulling material through that unfavorable equilibrium because of how favorable the second reaction is. So you essentially using Le Chatelier's principle here. Okay, so we're going to, just to recap, we're always going to end up where the most stable anion is. So whether we're doing a SNAc reaction, in this case where the leaving group is highly, highly stabilized, right? So we're going to end up here. If our starting materials contain the most stabilized anion, we don't really ever get started. We've got a little equilibrium here. Or, in some cases, our nucleophile is a really pissed off anion or something like it, like a Grignard reagent. And in that case, we actually end up, in a lot of cases, getting stuck at basically a tetrahedral intermediate because there's nothing I can eliminate that doesn't have a horrible, horrible anion stability. Okay, so like I said, we're going to be focusing most of our discussion on this scenario. We've discussed irreversible additions in SLO6 and SNAc reactions in SLO5. Okay, so the last thing I want to do in this video is to give you a sense for a few commonly observed reversible additions. You might be wondering, like, why we care about these reactions at all, because they're not favorable. We're not going to be making products using these kinds of processes, at least not yet. But it turns out that there are some that are biologically relevant and that there are some that are worth knowing because we've actually discussed them before as models to understand carbonyl reactivity. So the first of these is what we're going to call the hydration of a carbonyl. Typically we'll see this for aldehydes or ketones. So carbonyl hydration. So this sounds a little bit like what you might expect. We're going to add water. The way if you hydrate after going to the gym, you add water. And I'll do this with an example ketone. Like I said, you could do this with aldehydes also. And so in this reaction, we're actually using water as a nucleophile. And this water will add, the oxygen will add to the carbon of the carbonyl. That will break the CO pi bond and make an O-. But we could actually, if you draw this out mechanistically, I'm not going to do it on the board, but it's good exercise for you. If you draw the product of addition of water to the carbonyl, you'll see that there's an intramolecular acid-base reaction that could happen. And you end up distributing the protons of this water molecule such that you end up with two alcohol groups on the same carbon. So this carbon here was the carbon of the carbonyl. And so we call the product structure a hydrate. So essentially it's the product of hydration. And because this came from a ketone, we're actually going to call it a ketone hydrate. You can imagine if you did a similar kind of a reaction with an aldehyde, you'd call the product an aldehyde hydrate. Another option would be to actually change your nucleophile slightly. So instead of a water molecule, you could imagine an alcohol or some other kind of an OH functional group. So we can make what are called hemiacetals. So hemiacetal formation. So again, I'll change this to an aldehyde just to give you a sense for different kinds of structures. And so we could choose whatever alcohol we want. Methanol, keep the structure small since my board is not particularly significant in size. So we know the alcohol oxygen is nucleophilic. That's going to add to the carbonyl. That'll break the CO pi bond, make an O-. And again, if you're writing out these mechanisms on scratch paper, strongly encouraged, then you will see that you can transfer a proton so that you have no charges. So in this case, we have this kind of a structure. So essentially it's an ether that has a carbon also involved in an alcohol. So this is called a hemiacetal. Not hemiacetal. Remember, acetyl groups they're different. Those are the things that we're transferring around in SNAc reactions. And then the final compound that I want to talk about are called cyanohydrins. So these are reactions where rather than using CN-, we'll use HCN. So this is the hydrogen cyanide, that highly toxic compound. And so we'll look at another aldehyde. And HCN. So this is a weak acid. Remember, this is a compound that would have had a pK of 9. And so at some level, this proton dissociates. So you have a little bit of CN- and some protons floating around. And that actually gives you a reaction to give the addition product. So CN- would be the nucleophile after this compound dissociates. Adds, makes O-, and the proton is captured. So we have an OH group and a nitrile. So really what I wanted to mention with the cyanohydrins is, one, to give you a sense that these kinds of reversible additions don't just involve oxygen nucleophiles. They could involve carbons, for instance. This is a pretty specific case. But also that these cyanohydrins are actually present in small concentrations in the pits of some kinds of fruits. Sorry, cyanohydrin, not cyanohydrins. I can't write and talk at the same time today, apparently. And so this is actually kind of an interesting idea where if this reaction is reversible and you eat some of this, like maybe you accidentally eat the pit of a peach or something like that, or a cherry, you would actually end up making HCN again. And so there's some thought that there's the evolutionary processes that have given rise to like plants that have what amounts to like a chemical warfare agent in their pits is a chemical defense. Right? So they're actually using this reversible chemistry to poison organisms that decide to eat their seeds.